I'm Aki Fujimura of D2S. Co-author is Ajay Baranwal. Ajay presented yesterday. He is the Center Director of the Center for Deep Learning in Electronics Manufacturing. CDLe is what we call it. CDLe.ai is the website. CDLe is a collaboration of Newflare, Micronic, and D2S together in San Jose, with assignees from each of the companies working together with deep learning experts, 3 of them under Ajay, to 1, create core competencies inside of each of the companies in deep learning, and 2, do deep learning projects that can make some differentiating feature for either products or services of each of the companies. It's been pretty successful over the last 3 years. We've created more than 30 projects, graduated more than 20 students, and each of the companies are in the process of productizing some of these technologies right now. In the process of getting there, we had some successes and some not so successes, and we've learned a thing or two. We want to share kind of a recipe that we stumbled upon to make deep learning projects successful in our unique industry. Now, deep learning is a purely pattern matching based statistical automatic programming technique. And it's been tremendously successful in the world at large, particularly in social networking arenas. Companies, entire companies, are valued based on how much data you have, because deep learning needs lots of data. Right? So people have figured out that if you have lots of data, because we have deep learning, you can do tremendous stuff. So data is incredibly valuable. Companies are valued based on how much data they have. But it's not just social networking companies, industrial companies around the size here, and they all are using deep learning in very innovative ways, in a way that computer scientists doing the best computer science before 10 years ago couldn't touch. It's not just because computers are more powerful. It's not just because GPUs are getting much more powerful. It's not just because of that. It's because of deep learning itself. TU on the upper left-hand corner, you might not be familiar with. That's too simple. They are a San Diego-based company that is doing autonomous driving for trucking, for the trucking industry. They currently operate in Arizona, New Mexico, and Texas. So deep learning has been successful in world at large for sure, right? There's no question about that. Why? What's special about semiconductor manufacturing that it doesn't seem to be, as much momentum behind deep learning? I say that, but there's a lot of papers, even in this conference, and there's a lot of papers on deep learning, and many of these companies talk about production deployment. But when we do a luminary survey in our industry, as eBeam Initiative does every year, this report, by the way, is available in ebeam.org website. We ask, how long is it going to take, basically, before deep learning becomes a competitive advantage for any step in the mask-making process? Right? And last year when we asked, people said, yeah, it's definitely going to happen, but 2 to 3 years from now. This year when we asked, they said again, it's definitely going to happen, but 2 to 3 years from now. Right? So this is kind of very similar to how EUV looked for a long time. It's finally happened, of course. And the question is, well, how long is it going to take for deep learning then? Right? Is it ever going to happen, or is it just going to keep slipping? Well, I'm a believer. I really think that deep learning is going to also revolutionize the computing aspects of this industry. I just think it takes a long time to make it happen because productization takes time, particularly in a quality-conscious culture like our industry, of course, has to have. Prototype is easy, production is hard. To bring that home, we have a video here. Ajay Barambo, my co-author, has a son, Tanish. He's a senior in high school, and he's a whiz kid. He's a particular deep learning whiz kid for sure. He ran a summer course in deep learning for other kids. And one of the students was Teddy. He is 10 years old.
Hey, Daddy, what you doing?
I was just making a deep learning algorithm that Tanish taught me, and I just want to see if it can successfully predict that Snowball is a cat.
Okay, sounds good. Are you doing it now?
Let's see if it works. So, like right now, it's loading data. It says Snowball's an Egyptian cat. It's not an Egyptian cat, but it's a cat, so it's not too far off.
Yeah, that's not too bad.
Yeah, and you can see it says 20%, and it's not very sure because the database that I'm using only has around 1,000 pictures, and it doesn't even have the correct species that Snowball is.
Okay. Was it easy to do?
Oh yeah, it was very easy. You can see it only has like 30 lines of code, and TensorFlow, it already has pre-built neural networks, like in this case ResNet 50, and that makes it very easy to learn.
So if it's so easy, do you think like we can make an iPhone app or something and sell it, make lots of money?
I don't know. That might be hard because I only know how to do the deep learning part, not the app part.
Oh, I see. Okay, thanks, Daddy.
Okay, thank you. Bye.
So, one of the things that Teddy said is very important. He only has 1,000 data, and he needs to get more data. Data is absolutely critical for deep learning. That's all it knows, really. But data is very hard to get in our industry. If you're a mask maker, you have lots of data. But if you're a vendor to the mask maker that might want to do a deep learning project, the mask maker can't give you any data because it's not even their data. It's their customer's data. That's a big problem. But even for the mask shops, it's very difficult to get enough anomalous data. A mask shop's perspective might be that we have tons of anomalous data. We shouldn't have this many errors, but we do, and we have to repair them all, right? But it's not enough. For deep learning to be successful, particularly in anomalous situations, it needs to have hundreds and thousands, and maybe even 10,000 of one particular kind of a defect or anomaly. It's very difficult to get that kind of data. And not only that, you have to be able to have new kinds of pictures, like what Teddy went through just now. Egyptian cat, it's not an Egyptian cat. Oh, it doesn't have, the training data set doesn't have the right kind of cats in it. He has to go get the right kind of cats in it to train the neural network the right answer. Same thing happens when somebody is trying to go from a prototype to a production software, and the production system needs to be, let's say, 94, 95% accuracy, and you only have 92% accuracy. Well, to get that extra 2 or 3% accuracy, you have to be able to diagnose what it's confused by, what the network is confused by, and go generate data. But you can't do it by creating an anomaly, test printing, doing some measurements. You can't be doing that, right? So the only way that we can reasonably do deep learning and succeed in those kinds of deep learning projects is to be able to generate data yourself in simulation-based or deep learning-based digital twins. You have to spend the time to create the digital twins first so that you can create any kind of data at will. And that's how you can make deep learning projects successful. Our industry also has the quality requirement. Of course, 7 sigma is not sufficient in our industry. Deep learning is a statistical method, so it will make mistakes. There's no way it's going to be 7 sigma. It can be better than human, that's not too hard. But 7 sigma, no way. The key here is to apply deep learning judiciously. You need deep learning to be able to do something, and then afterwards, you need something else to be done. That's also the point of this slide. Deep learning is a black box, right? So if you run deep learning to, let's say, do something like, mimic NPC or something, and typically what you can do is to make the network good enough that it can be like 3 or 4 nanometer accurate. That definitely can be done. And you need like 1 nanometer accuracy, so it's not good enough. But when you run 100 test cases, the worst case will be, let's say, 3.7 nanometers. But when you run the 101st one, are you sure that you're not going to get 3.8, 3.9, 4.1, 4.3? You can select the deep learning neural network in such a way that it will not make egregious errors. You can do that. But there is no proof that you can provide. There's no algorithmic check that you can provide that can say it's never going to be 4.2. Right? That lack of assurance is very difficult in our industry. So the only way you can really deploy deep learning successfully in our industry is to have deep learning as a component, but have something else that follows that is either maybe a human that takes the result and does something with it and uses humans' own judgment, or has analytical tools that actually can take the results of deep learning and do something else with it to maybe correct it. So I want to get to the recipe part of the talk. Every recipe has ingredients and they have a procedure, right, that you follow. So this is the ingredients part of the slide. The number one ingredient that you need is an executive sponsor with a long-term commitment to deep learning. It's long-term, not just short-term, because a prototype is so easy to get the interest short-term, and then it takes a long time to make it into a production thing. And I think in some cases, there might not be enough patience. Oh, prototype was so easy, but hey, it's taking too long. It's not working out. Maybe deep learning just isn't the right thing. That kind of a doubt creeps in. It just takes time. Well, not just takes time. It takes other things too, other ingredients too. You also need a lot of dollars because you need a lot of computing resources to succeed. Petaflops of computing, $1 million computing budget is what you need. You can do the prototype in a desk side, one GPU system like Daddy did. But in order to do production level systems with million data, hundreds of thousands at the very least data, and train it many, many times, and in a quest to go from 92% to 93% to 95% accuracy, you need petaflops of computing. And you need that computing not just because you need to do it for deep learning training. You also need it because you need to generate the data with digital twins, maybe simulation-based, maybe deep learning-based, but all of that takes a lot of resources too. But money and data, that's not the hardest part. The hardest part, the thing that takes the most amount of commitment, is people. in our experience at CDLe, the only way to successfully turn a domain expert that come in into a domain expert that also knows deep learning very well is if they have an immersive experience. It's immersion, not like 193i kind of immersion. It's immersion like language acquisition kind of immersion. You need to forget about other work and focus on deep learning for 3 to 6 months. If you do that, you can become a deep learning expert. But part of the ingredient for success there is because you may not already have a domain expert that is also a deep learning expert, but because deep learning is totally data-based, domain experts are absolutely required. You can't go and hire deep learning experts and expect them to become domain experts overnight, and you don't have domain experts that are DR experts. So the only way to make it successful is to couple domain experts with deep learning experts. And that's exactly what we did at CDLe, and that was one of the best parts of how we set it up in retrospect, is that we have 3 deep learning experts coupled with domain experts from each of the companies. And that combination not only trains the domain experts with deep learning so they can go back to their companies and be the deep learning experts in their respective places, but also they can make a successful project by combining the talents of 2. It's teamwork. And those are the ingredients, but the process is also important. The first step, essential step, is selecting the right project. I'll talk about that in the next slide. After you select the right project that's suitable for deep learning, you have to select the right kind of a neural network. There's a whole bunch of them available, and once you get more advanced, you need to be able to custom create new networks that are more appropriate for the task that you're trying to perform. This is very critical. Some networks can succeed, some networks won't. If you need to have bounded errors, you need to pick the kind of network that will have bounded errors. And these are important criteria for how you set things up. The important step I already talked about is creating digital twins. You need to take the time to craft the digital twins or acquire digital twins somehow and be able to create the data at will, the kind of data that you need at will. That's what you have to do to be able to get to production quality of deep learning network. And finally, you have to have the time and you have to allow yourself the time to fine tune. The last 10% might be 90% of the total effort. It might even be the last 5% is 95% of the total effort with deep learning. Deep learning projects being productized is certainly not any easier than software projects or hardware projects. It might even be harder because you're manipulating data and you have to collect data. The first step on selecting the right projects, I want to get into just a little bit. One thing that's really important is not to ask deep learning to do the impossible. It is a statistical technique, so it will make mistakes. So only using deep learning to try to do IoT, MPC, or MRC, that's not going to work. You need something to check the result or improve the result later. But it's extremely useful for acceleration, initial condition acceleration, for iterative optimization like IoT, MPC, or anything else. It's also good for estimation of other tools when all you need is to be approximately right. Deep learning is incredibly good at that. It's amazing what pattern matching can do without actually computing anything, right? Prediction algorithms are good too. So if you want to do a hotspot analysis and it's an approximate answer anyway, then a deep learned version of MRC might be useful for that. Also, MRC output and other verification output like automatic defect categorization for inspection. Those are excellent deep learning applications. Another thing on E-beam little simulation here, I saw a presentation once that talked about saying, hey, I was able to make a deep learning network that can mimic E-beam simulation to 3 nanometer accuracy. That's true, you can do that. It's just a question of how useful that is. It's a very interesting deep learning exercise to be able to do that, but I don't think it's very useful because E-beam simulation, which is a Gaussian convolution, or little simulation, which is a fast Fourier transform, these are incredibly fast on a GPU. And their answers are the golden answers. Their answers are the simulation answers that you compare deep learning results to. And so you can't be more accurate than the golden answer. So it's faster and more accurate to do it in the analytical way. So you have to be careful what you pick as a deep learning project to do to make sure it's useful. Now, I just wanted to highlight 3 examples of deep learning projects. And when I saw SPIE advanced lithography earlier this year, I saw this paper from Canon, and I was very impressed. It's an incredibly good paper, and it happens that they're presenting after me. So please listen to that presentation. It's a very impressive deep learning application. ASML Brian and Yukao presented 3 years ago, maybe 4 years ago, at this conference, and they have a product called Neuron with NEW, just like spelled like Newton, right? Very clever name, I thought, very typical of Yukao. They did OPC and used deep learning to be faster and also more accurate at the same time. Different deep learning networks did different parts of it, but it's very impressive deployment of deep learning. Now, after that, Synopsys has also published lots of papers on deep learning deployment for IoT. So it's not just ASML, but it was the first I heard, and it was very impressive. Yesterday, my co-author Ajay Baranwal presented this paper from New Flare and Center of Deep Learning, CDLe, and it's also a very impressive result. Using a 26-layer, 12 million node network being trained by 800,000 data points, many of those created by digital twins that were crafted also with deep learning. They were able to create a 90+% accurate LiDAR failure diagnosis tool. So it takes a picture of, well, it doesn't take a picture. You take a picture of a failure like you're looking at now, and then you say, well, what's likely to be the cause? What's likely to be the problem in the machine that would cause a picture like this to happen? Is it a dose error, shape error, position error? Knowing that helps the application engineer diagnose, the system engineer diagnose the problem and be able to make the fix to the problem earlier than otherwise possible. Very important result, I think. And 12 million node network. That means 12 million parameters, right? You know, I think many of you know that mask models, very sophisticated mask models, have 10 to 20 parameters in it. And it's very difficult to optimize that to get the optimal results. 12 million parameters. Of course, it takes a lot of data to get that right, right? The only way to succeed in projects like this is to have digital twins. So getting back to the recipe for success, both the ingredients and the procedure. I'm not going to repeat the recipe here, but one thing I want to say is I really believe that 100% of the customers or companies in the mask making community can benefit from deep learning one way or another. If you haven't thought about exactly how it can be done, I think you need to keep thinking. We'd love to help you think through that too. Deep learning is a major discontinuity in the world of computing. In fact, I think of it like this. Long time ago, 30, 40 years ago, software became important, right? Everything used to be done with hardware, but software working on microprocessors became important. And now all the hardware companies had to hire software expertise in-house. Instead of just outsourcing it, they needed to build software expertise, and that became an important part of how you become a better vendor than your competitors. Right? I think the same thing is happening right now. Deep learning competency built inside your companies is now just as important as building software competency was 30, 40 years ago. And because of that, you need to make an executive commitment and pick the right project and then stick with it to make it successful. We would love to help with that process. If you have any questions about it, please come ask us. Thank you very much.